Okay. Hello and welcome. So, what's cooking in Trusted Firmware M? That will be the topic for today. My name is Miklós Bálint. I'm from ARM's open source software group. And so, let's start with a quick recap of Trusted Firmware M as a project. It's an open source, open governance project. It is an implementation of Platform Security Architecture, PSA. It was launched 1 year ago at Linaro Connect in Hong Kong. And we have now, in this 1 year, we are working on 2 flavors of the secure partition management design. We have dual core support investigation ongoing. We are looking at interrupt handling, and many more hot issues are on the plate for this year as well. And what we are aiming for is wider coverage of use cases than we had in the last year, and we are looking for collaborative development. So we're looking for everyone to get in the kitchen. So let's look at PSA security domains. That's the foundation of everything that we do. So the basic isolation is to create a secure processing environment to isolate the security-aware aspects of the system. And so that is the foundation of isolation. That is level 1 in PSA. In several use cases, it's beneficial to have a more stringent isolation scheme on the secure side. And the first step in that is to create a protected trusted compute base where we separate the root of trust from the secure partitions in the system, which are doing regular processing of secure requests. And in some use cases, it's even beneficial to support multiple tenancy to isolate each secure partition from one another. This way we ensure complete isolation of various features in the system. PSA also recommends, although it doesn't mandate, isolation on the non-secure side, and that is of course beneficial for compartmentalization of threats even in the non-secure application. And it's also beneficial because if we can identify non-secure threads, then we can assign different access policies to secure assets to the various non-secure threads. One of the big topics for this year in Trusted Firmware M is that last year when we announced version 0.1 of Trusted Firmware M, of course, we were focusing on the basic isolation, level 1 isolation. This year, higher levels of isolation are definitely on the plate, so we are actively looking at level 2 isolation, and we have had a proof of concept for level 3 isolation, but that is very rudimentary. It's basically a thought experiment that we have in the code base to check what problems we encounter when doing higher levels of isolation. But we are actively looking at level 2, and we have the design there. Let's look at the different implementations that Trusted Firmware M offers, because we have several flavors of Trusted Firmware M, and the one that we discussed last year and what we created last year is where secure services are implemented as functions. This implementation is native to ARM v8M architecture. In this case, the interaction between security domains is based on function calls, and this creates a sort of library-like programming model on the secure side. So secure services are provided as sets of secure services are provided as libraries that can be called as functions from the non-secure side. Design work currently is focusing on various exception handling scenarios. I will talk about those in more detail later. And we are also considering, but it's a very early work, we are considering how we can do dynamic allocation of secure resources in this case. So for example, if we have multiple concurrent threads, multiple concurrent requests from non-secure threads on the secure side, we allocate a separate secure context for each of them, but we don't reserve space if there's no active request. So when, for example, thread 2 completes execution of secure services X, Y, and Z, and execution is returned to the non-secure side, then we can free secure context 2 and we can reuse that for subsequent calls later on. And we're looking at the ramifications of that. And of course, in order for us to be able to handle concurrent requests from the non-secure side, we need to have an awareness of what non-secure thread is executing and is making the request. This in the case of so this can be done in multiple ways. We have CMSIS defining trust zone context management functions where the non-secure RTOS can give a notification to the secure partition manager on context changes. And so we can use that information. The other big implementation of partition manager and interaction is the IPC model, where secure partitions are implemented as threads. This is a more robust, more prescriptive framework. It is architecture agnostic, so it doesn't rely on ARM v8M specific features. So it is well suited for different models of isolation. Here we have static allocation of secure resources. We have secure threads that are created at boot time, at initialization. And so interaction between the security domains is based on connections and messages. Here, the design is well established in PSA firmware framework, which is at version 1.0 beta. And now we are looking at various potential extensions to that framework on how we can create a more flexible framework in this model. A big topic that we are also looking at this year is to support physical isolation of secure and non-secure processing elements, so basically a dual core design. In this case, we have a platform-specific set of shared resources, and we have concurrent execution of secure and non-secure processing elements. They execute independently, and here the programming model can be the same as for single core implementations for higher levels, so non-secure threads and secure partitions can interact using the existing APIs that we have defined for a single core use case. But of course, design work is going on for defining an appropriate level of abstraction of the interaction of the two cores in this case. So, as promised, I want to take a closer look at exception handling and the various scenarios that come up. And this is geared towards the single core use case because that presents the most challenges in this respect. We have all the players on a single processing element. We have the non-secure application. We have exception handlers on the non-secure side. We have the regular secure services which are running in secure mode but potentially are unprivileged. And of course, exception handlers on the secure side are privileged and they form part of the trusted compute base. And there are all sorts of transitions between these states as results of interrupts, and we have to look at all of the implications of those for our implementations. So first of all, let's look at the case when we have non-secure execution interrupted by a non-secure interrupt, and what that means for us. Actually, that's fine. We don't have to concern ourselves with that, since there are no secure implications. On the other hand, if a secure service is interrupted by a non-secure interrupt, now there are all hosts of considerations that have to be made in order to make sure that security is not compromised in the system. First of all, the secure state consistency has to be ensured. And in the case of ARM v8M, the foundation of that, the principle of that, is so the essentials are provided by the hardware, registers are stacked and cleared before transitioning to non-secure handler mode. But of course, if a context change, so if there's a context change as a result of the non-secure interrupt, and so the new non-secure context wants to enter the secure domain, then we need some sort of a notification from the non-secure RTOS to TFM about this context change. As I previously mentioned, we have a proposed way of doing that, but it definitely has to be handled correctly. The other big issue in this scenario is the starvation of secure services, and here the first approach that we can take is to live with it. This is an appropriate course of action if we say that the secure service was running as a result of a non-secure request, because in that case the non-secure handler is actually starving a non-secure thread execution, and so that may be okay in some scenarios, but in some other scenarios, in case there's a critical operation on the secure side, then of course this cannot be permitted, and in those cases secure execution priority needs to be boosted, or alternatively there must be a watchdog on the secure side to limit the execution time permitted for non-secure exceptions. Secure interrupts, from a context management aspect, this is more straightforward. It is more easy because TFM is anyway the owner of secure privileged code. It's always in the trusted compute base, and state management is therefore treated by trusted firmware M anyway. But secure privileged interrupt handlers pose a problem. They have unrestricted access to all secure resources in the system, and that can pose a problem. If we observe the principle of least privilege, it is beneficial to have the interrupt service routines executed in a secure container with unprivileged access to resources, and only so the interrupt service routine has access only to the resources it definitely needs. The question is, how can we do that? And we can do that by deprivileging the secure interrupt, and this is the way device drivers can be compartmentalized on the secure side. This is also beneficial if we have third-party secure partitions that want to have their own device drivers, or if we simply want to protect the trusted compute base from programming errors in our own device drivers. So the way it can be done is the privileged interrupt service routine that is triggered by the exception will enter trusted firmware M, but that is only a wrapper which calls a partition manager, which creates a sandbox, and the sandbox is activated by an exception return to thread mode keeping the priority of the original interrupt, but executing in unprivileged thread mode for the duration of the secure partition interrupt service routine. When this operation is done, all of the sandbox can be unstacked and the original context can be restored with the original sandbox if needed. So, to summarize, TFM design is, in TFM design, there's no one-size-fits-all. We have all sorts of ingredients. We have isolation, we have execution, we have interaction, we have exception policies. All of these depend on use cases. All of these depend on restrictions and of course the threat models that we want to support in a particular use case. And so Trusted Firmware M is aiming to provide a scalable framework covering as many of these use cases as possible, but of course flexible configuration is key to achieve that. Status on some of the issues that I mentioned. So shared memory model and IPC model, now both are supported by TFM's SPM depending on build configuration. Secure services, we have the basic secure services implemented for the shared memory model. Their porting is ongoing for the IPC model. We have in the isolation domain, we have level 2 design RFC published. It is publicly available. And we are waiting for feedback on that, and we are hoping to get some feedback on that. Secure interrupt handling, we have a design proposal for that, and the implementation is on public review. In terms of multiple context management, we have some context awareness design and prototype published, but preemption from the non-secure side and concurrency are at the design stage, so we are limiting flexibility there at the moment, but we are actively looking at how we can enable more use cases in that respect. For modularization and dual core support, we have several design documents on review. Proof of concept work is ongoing, and the next talk in this room will discuss more on this topic. And so, how to get involved? We have an offering of all the buffet meals that are ready in our Git repository. We have some master chefs attending the conference, so you can get in touch with them. And so you can come around to the light hacking room on Thursday, schedule a meeting, contact us, or subscribe to the mailing list. And so all I ask is that all of you join us in the kitchen. We can sure use your help. And I think we do have time for questions.
In terms of the level 2, the RFC, I haven't had a chance to look at it yet. Do you get into how the chain of trust is passed along onto the application to the secure functions and how that's maintained, or is that considered out of scope?
So currently our primary focus is on the IPC model for level 2 isolation. I'm not sure what you mean by chain of trust. So what policies do you mean?
I mean how the key management would happen between the different components if they're coming from different entities, and that one entity is providing the platform level and one entity is providing the application level for the secure side. So
I should say that the chain of trust is part of the boot flow. We have a signed, attested secure binary, and that secure binary still contains all of the the partitions on the secure side, and so their state is attested to from the boot onwards.
Okay, but could it possibly happen that different parts of that are signed by different entities, so that the platform is signed by an entity and then?
We are not at this point addressing that. So,
Okay.
yeah.
Feels like with a lot of the interrupt stuff that there is hardware support that would reduce that complexity significantly. Is there any plans from the ARM architecture to try to address that?
So, the fundamentals for exception flows are provided by ARM architecture in V8M.
I understand that, but I think this goes like, so if you think about like virtualization on desktop server class systems and so forth, there's a lot of iteration of architectures that occurred, IOMMUs, things of this nature over time towards whether it's performance optimization. So yes, the fundamental ability is there. My point is there's a lot of software complexity because hardware is probably not providing enough assistance. So for example, the fact that you need to do OS notification is not something that you really should have to do. Right, that's because the hardware is, in my opinion, missing a feature, right? Because the isolation, information isn't being provided or something of that nature. So that's the question about improving the architecture so that over time these things are, better.
What I can say is that, of course, definitely it's being looked at. It's always a compromise, because these are microcontroller complexity designs and architecture, but I'm quite certain that it's being looked at actively for newer iterations of the architecture. Thank you. I have confirmation to say that it is being looked at.
Work's going on.
Yeah.
Yeah.
Yeah, you have to remember the secure, non-secure stuff. 8.0 was the first version.
Understandable. That's the question that, yeah, that.
And the hardware all across.
Exactly, right? As we build software and we realize, okay, it's a continual process, right? So I'm not just wanting to ask the question that, yes, it is being, yeah, so.
Okay. Anyone else? Oops. In that case, thank you.